this video, we're going to talk about a few examples of taking limits of multivariable functions by taking advantage of their continuity. And then I'm also going to kind of wrap up with an example talking about what it looks like when a limit does not exist for a multivariable function. So I'm going to go ahead and just jump right in. The main idea behind this is actually pretty similar to when you're working with just like the single variable functions. When you're working with continuity, the idea is that if you're not going to get in trouble plugging it in, like dividing by 0 or something like that, then you can just plug it in. So that's what we're going to do. In this example here, we have the limit of x and y approaching 5, 6 of x minus y and x plus y. So to evaluate this limit using continuity, all we have to do is note that by plugging 5 and 6 here at the bottom, we're not going to wind up with 0. And we also know that the top is just always continuous, so that's totally fine. So we're good to use direct evaluation in this case. So that 5 minus 6 divided by 5 plus 6, that's just going to be equal to -1/11. So that's pretty straightforward. In our second example, we take the limit as x, y approach 0 of 4x squared plus 10y squared plus 4 divided by 4x squared minus 10y squared plus 6. So once again, by plugging in 0 in the top and the bottom, we're not going to wind up really like dividing by 0 or winding up with anything like that. So we're able to just go ahead and plug in zeros in all the x's and y's, and we wind up with 4/6 as being that limit. Our third example is the limit of x, y approaches pi over 4, 1, y times tangent of x divided by 1 plus y. Okay, so plugging a 1 in for y here doesn't give us 0 on the denominator. And the other thing that we have to watch out for is that sometimes tangent is kind of discontinuous at certain values. But if we plug in pi over 4, that's not going to be one of the values. Tangent of x at pi over 4 is just equal to 1. So we can plug everything in directly. We get 1 times 1 over 1 plus 1. So that's just equal to 1/2. So as long as you know that everything's continuous, you're not going to get divide by 0 problem or, square root of a negative number or anything like that. You're good to go to just go ahead and plug in the values that you are approaching and use that to evaluate your limits. But I do want to show an example of what happens when a limit doesn't exist. So if we have the limit as x and y approach 0, 0 of x cubed times y over x to the 6th plus x, oops, this should be a y squared. We kind of have some red flags right off the bat because we're dividing by 0. Now, generally speaking, we can try to apply some rules that we might have learned in like Calc 1 where we're able to cancel things out or something like that, and we get the problematic pieces to go away. But there's not really any opportunities for things to cancel or to rearrange or anything like that. So we should know pretty well off the bat that this is going to wind up not having a limit that's very cooperative, I guess. And the way that we're going to check that is by testing along 2 different directions for the limit. So we're going to test with a path y equal to x, okay? And what this means is that we replace all the y's with x's. So what this problem winds up looking like then is limit of x approaches 0, 0 of x cubed, and then we replace the y with another x, and then x to the 6th plus now x squared. We're able to kind of simplify some things down, right? Because we're going to wind up with limit x approaches 0, 0 of x to the 4th divided by x to the 6th plus x squared. And we're able to take an x squared out of each of these terms. So you get x squared divided by x to the 4th plus 1. And at this point, we're actually able to directly evaluate. You plug in zeros for all the x's, and you just get 0, because you get 0 over 1 here. So that's if we approach it from one direction, we're going to get y equal, or from the direction y equal to x, we're going to get 0. But when we're working with limits of multivariable functions, we want to make sure that the limits agree from every single direction we could possibly think of or, even do. And well, one maybe kind of quirky direction is the y equals x cubed direction, okay? So if we plug in x cubed for all the y's, our limit now, or our function now becomes x cubed times x cubed divided by x to the 6th plus x cubed squared. So we can kind of simplify some stuff down here. So x to the 6th divided by 2 times x to the 6th is what happens when I combine those two things right there. So I'm able to cancel out the x from the 6th from the top and the bottom, like so. So what we're going to wind up with, there's not really even any x's left to plug zeros into. We just get 1/2. Well, this limit is not equal to this limit. Even though it's of the same function, approaching it from two different directions didn't give us the same result, which this is kind of a similar idea to using like the left-sided limits and the right-sided limits that you learned in Calc 1, where you want those two sides to agree. Well, that's what we need here, but they don't agree. So the limit does not exist. Okay, so like maybe like the idea and the computations and stuff are all of that are pretty straightforward, but a really common question is, okay, how do we choose what directions to try to approach from? So you always want to try to pick a direction to approach from that, maybe might be a little bit, might simplify down to something that's a little bit different. And the way that you check to see if something is, or not really check to see, but try to pick something that would simplify down nicely is look to see what you've already got in your existing structure, right? Like we have a singular y here, and we have some y equals x is always a good one to start with, to be honest. So you can definitely always go for that. But another really good one to look at is just check to see what's already in here, right? If we contain like an x squared, then maybe using the path y equals x squared would be a good one to go for. Or here we had the x cubed and that x to the 6th, and that's something that they both have that the 3 sort of in common as a factor. And so setting y equals x cubed is a really great place to start because we already have this kind of cubic behavior in our function that we're working with. So just something to kind of keep in mind as you're trying to figure out, okay, what direction should I try to approach this from to show that the limit doesn't exist? Maybe think a little bit about what's already there and what you can replace it with. So that's pretty much it to this video. Like I said, taking limits is reasonably straightforward as long as either they're already continuous or you know that the limit doesn't exist. So that's pretty much it for this one.